Hi, in today's video, we're going to be talking about the addition of acids to alkenes. So as a reminder, alkenes are sp2 carbon atoms that are bound to each other, and they have a pi orbital between the two. It's highlighted in this case in blue. So an addition reaction is when you have a pi orbital becoming two sigma bonds. And so in this case, you formed a bond to X and a bond to Y, highlighted in purple here. So let's look at how an alkene reacts with an acid. And this is going to tell us a lot about how alkenes react in general. So the first thing an alkene does, or the first way to think about an alkene, is to remember that when other molecules interact with acids, it's the acid that is acting as H+. And so therefore we're looking for a nucleophile, or electrons, on the other reaction component. In this case, this is an alcohol that's been shown. So similarly, it's the electrons in the pi bond that are going to interact with or react with the proton. And so it's going to break the hydrogen-chlorine bond and form a new carbon-hydrogen bond. This generates a carbocation. If we highlight where the protons are on this molecule, you can see that this carbocation has two hydrogen atoms and a carbon, and this is a carbon-carbon bond. I've now highlighted the hydrogen from the acid in purple so you get a sense of where it is. It's really important to keep track of those hydrogen atoms. So now you have a chloride and a carbocation, and this is just like SN1 chemistry, substitution chemistry. And so you form your new carbon-chlorine bond. I'll point out that this particular carbocation is a primary carbocation, and so it's really not stable. This is just kind of an example of how the reaction occurs, but it is very hard to react with a simple alkene like this. So let's look at some other examples. And a key challenge with alkene reactivity is to pick what side is going to react and where the nucleophile is going to wind up at the end of the day. So again, if we treat this alkene with HCl, there are two possible outcomes for what carbon can be protonated. You could protonate the central carbon and get a primary carbocation, or you can protonate the terminal carbon and get a secondary carbocation. So again, I'll highlight that with purple to highlight where the hydrogen atom is that came from the acid. And as you remember from our carbocation stability video, the secondary carbocation is significantly more stable, and so therefore that is where the reaction occurs with the nucleophile. This is called the Markovnikov product. So you'll hear me refer to the Markovnikov product, and that is simply the product that came from the more stable carbocation. So now if we look at this alkene, again we can react with HCl, and in this case we get a secondary carbocation. For this particular alkene, both of the carbocations are secondary, and so they will simply react with the chloride to give you this butane product. I'll point out that we would not necessarily call this the Markovnikov product because both of the carbocations are identical. Now in this final case, you again have a situation where there are two possible carbocations that can be formed. You have a secondary carbocation and a tertiary carbocation. The tertiary carbocation is significantly more stable, and therefore that is going to be the Markovnikov product that you observe. So it's possible to add other weak nucleophiles to these types of systems. All the nucleophiles in acidic solutions are going to be weak because they're not going to have negative charges. Well, the chloride will have a negative charge, or the iodide or the bromide will have a negative charge, but you will never have oxygen with a negative charge under these strongly acidic conditions. So in this case, we again can react, we can look at this reaction product of this alkene with HCl, and we see the Markovnikov product. If we added this in the presence of water, or if we added an acid in the presence of water, so now we have sulfuric acid. So the conjugate base, the sulfate, is non-nucleophilic. It's just simply too stable. And so now water is going to add as our nucleophile, and this is going to do SN1 chemistry or SN1-like chemistry. It's an addition, but the carbocation, you can think of those last couple mechanistic steps as SN1 chemistry. This will give you now this tertiary alcohol. If you did this reaction, and again, we can mechanistically think of sulfuric acid as H+. If we did this reaction instead in methanol, we would end up with this methyl ether product. And again, where the methanol is adding in to this tertiary carbocation, which is a common intermediate across all of these reactions. And if you have questions about how those mechanistic steps work for this, please look at the previous videos on SN1 chemistry or on the ether synthesis or alcohol reactivity videos posted in the previous chapters. Thank you for your time, and I look forward to answering your questions. Thanks.